So let's look at this first free response that was in 2015. If you look at these, the key is in the wording. You can use your calculator on them, and so that part's not difficult. So if you can figure out how to set it up, it's pretty easy. So if you look at this, it says the rate at which rainwater flows into a drain pipe is modeled by this function R of T in cubic feet per hour, and T is measured in hours from 0 to 8. And the pipe is partially blocked, allowing water to drain out the other end of the pipe. And so D of T is the function for it draining. So you've got a function for it flowing in and a function for it draining. And there are 30 cubic feet of water in the pipe in the beginning. So part A says how many cubic feet of rainwater flow into the pipe during the 8-hour interval from 0 to 8. So remember, anytime you're accumulating over an interval, it's going to be integration. So if you look here and you're talking about flowing in, you're just going to do 0, 8, your function. You're going to put it in Math 9, and you're going to get that answer. Very simple. So part B is the amount of water in the pipe increasing or decreasing at T equal 3 hours. Give a reason for your answer. Okay, so R of T is the rate of it flowing in. So you want, and that's not supposed to be a derivative sign, that's just supposed to be R of 3. So you want to get R of 3 either by plugging 3 in or looking it up in the table, and you get 5.0864. Then you want to get D of 3 because that's the rate of it going out, so 5.4. So if you subtract that, you get a negative 0.313632. So since the rate going in is less than the rate going out, it's decreasing at T equal 3 hours. Now part C is the key. They do this on all of these. Notice it says at what time is the amount of water in the pipe at a minimum. Justify your answer. First of all, keyword is amount of water. So that's the initial amount, then what flowed in minus what flowed out. Now, remember how you find a minimum is you set your first derivative equal to 0. So what we're going to do is we're going to make a function. And so our function, this will represent the amount of water in our pipe. So it start out with 30, we integrate 0 to whatever time, the flow in minus the flow out. So that's our function. Now, if we take the derivative of this, derivative of 30 is 0, and remember by second fundamental theorem calculus, if I take the derivative of this integral, it's just going to be this. So we'll set it equal to 0, use your calculator to find your intersection, and you will get at T equals 0 and T equal 3.271658. And don't round to the very end. Now what you want to do to find your minimum is you want to check your endpoints and your 0. So we already know 0 is 30 because that's our start. And at time 3.218, we're going to type in our calculator 30 plus 0 to 3.271658, R of T minus D of T. And of course, we'll type in our actual functions. And you'll get 27.9645. And then you're going to do the same thing at 8. 30 plus 0 to 8, your R function minus your D function, and you'll get 48. So of those three figures, the minimum is going to be at T equal 3.271658. So that's part C. Now part D, the pipe can hold 50 cubic feet before it starts overflowing. And it says for T greater than 8, water continues to flow. and it wants you to write but not to integrate an equation involving one or more integrals that give the time W when the pipe will begin to overflow. Well, it's going to begin to overflow once it reaches 50. So what you're going to do is just use your initial 0 to W, because they want W for the time, your flow in function minus your flow out function, and set it equal to 50. So that's part D. Now, let's look at the next one that's in your notebook. So this is the 2014 one, and it's talking about grass clippings are placed in a bin where they decompose, and for 0 to 30, the amount of grass clippings remaining in the bin is modeled by A of T, where A of T is measured in pounds and T is measured in days. So it says find the average rate of change of A of T over the interval 0 to 30. Indicate units of measure. Anytime you see the word average rate of change, it's going to be your slope formula. So if you look here, you're going to put A of 30 minus A of 0, 30 minus 0. Plug those values in. It's going to be negative 0.197 pounds per day. A of 30 minus A of 0, 30 minus 0, because you see the words average rate of change. Now, part B, find the value of the first derivative of 15. Using correct units, interpret the meaning of the value in the context of the problem. Okay, so you're going to use Math 8. So you're just going to use Math 8, put your function in, tell it 15, and you're going to get this figure, negative 0.164. And since it's negative, it means it's decreasing, and that's the derivative, so that's the rate that it's decreasing at 15 days. Now part C, find the time which the amount of grass clippings in the bin is equal to the average amount of grass clippings in the bin over the interval of 0 to 30. Okay, so first of all, notice the difference. It says average amount of grass over the interval. Up here it was average rate of change, so you use slope formula. Anytime you see average amount over an interval, you're going to use 1 over B minus A, which in this case would be 1 over 30, the integral of 0 to 30. And you're going to put that in your calculator, and you will get 12.415. So again, it says find the time T for which the amount of grass clippings in the bin is equal to the average amount of grass clippings in the interval from 0 to 30. Now part D, it says for T greater than 30, L of T is a linear approximation at T equal 30. It is a better model of the grass clippings remaining. Use this to predict when there will be 0.5 pounds of grass clippings. Okay, so remember linear approximation is a y equal mx plus b. So for that you need a derivative and you need a point. So you're going to do Math 8 at 30 and get that as your slope. And then you're going to look up 30 in your function a to get your ordered pair. Then in y equal mx plus b, we're going to put our y value, our slope, solve for b. And then when we get our linear approximation, it said you wanted to solve for t to predict when it's 0.5. So we'll put 0.5 in for y. We'll subtract this 2.86 over, divide by this, and you get 35.054. Again, just reading and making notice of the different wording. So let's look at this next one. It says on a certain work day, the rate in tons per hour at which unprocessed gravel arrives is modeled by G of T, where T is measured in hours from 0 to 8. At the beginning of the work day, the plant has 500 tons of unprocessed gravel. And during the hours of operation, the plant processes at a constant rate of 100 tons per hour. So, part A says find the first derivative at 5 and use correct units to interpret your answer. So, again, you're just going to use Math 8, plug it in, and you're going to get negative 24.588. So this is the rate at which the gravel is arriving is decreasing. So it already says this is the rate of it arriving, but that rate is decreasing at T equal 5 hours, and it's tons per hour. Now, part B says find the total amount of unprocessed gravel that rise at the plant during the hours of the workday. Well, the hours were from 0 to 8. You want the total amount, so you're going to integrate 0 to 8, put your G function in Math 9, and you're going to get 825.551 tons. Now, part C is the amount of unprocessed gravel of the plant increasing or decreasing at 5 hours. Show the work that leads to your answer. So you want to know what the rate of it arriving, so you're going to do G of 5, which will be 98.140764. So that's the unprocessed gravel. And then you're going to look at it goes out at a constant rate of 100, because it told you that up there. So that goes out at 100. So if you subtract that, the amount of unprocessed gravel is decreasing at T equal 5, because it'll be a negative number. Now, part D. What is the maximum amount of unprocessed gravel at the plant during the hours of operation? Justify your answer. So again, we've got to write a function for the total amount of the gravel. So it'll be 500 to begin with, 0 to T, the amount that arrives, and the amount that is processed out. So that difference would be the amount of unprocessed. So that's our function. Now, we're going to take our derivative to get our 0 to check for max. So if you take the derivative of 500, it's 0. If you take the derivative of this, it's just G of T minus 100 equals 0. If you put that in your calculator, you'll get that time 4.923480. So again, because we have endpoints and we have the derivative that we set is equal to 0, we're going to set up a chart. We know 0 is 500. We're going to do this in the 500 plus 0 to the 4.923480 of G of T minus 100 in Math 9. And then you'll do the same thing for 8. And you'll get those figures, and the maximum amount is at that time, but it asks for the maximum amount. So that would be the 635.376 tons. So make sure when you're checking the endpoints in the 0, you're doing it in this function that includes the initial. Now, review the next few in your notebook. Try to see what you can do, and then flip to the solutions that'll be behind it.